Hello, welcome. Today I want to talk a little bit about the dot and cross product. They're very useful operations that we can do on vectors that will solve many practical questions. But before we get into solving one of the questions, let me go through the criteria one by one. I can calculate the dot product of two vectors given by various representations, both geometrically and symbolically. What does that mean? If I have the two definitions written out here. One is the symbolic definition, and that is just multiply the components, add them up. And surprisingly, that's equal to taking the magnitude of A times the magnitude of B times the cosine of the angle. See the first question on the in-class activity for a derivation of why that is true. Um, but this is the symbolic way, and the geometric, of course, involves the cosine of the angle between the two vectors. So what does that mean? What does the dot product mean? That's really the meaning comes from the geometric way of thinking about it. The dot product is a scaled projection. So if I think of A dot B, thinking about this, drawing a triangle here from the tip of A onto B, we get that the adjacent side of this triangle, this is a right triangle, that will be the magnitude of A times cosine of the angle between A and B. How is that? How is that true? That's just a little bit of trigonometry coming. If you think about a unit hypotenuse triangle on the unit circle, the base is given by cosine, the height by sine, and scaling that by a factor of a. So the hypotenuse here has magnitude a. We get that the adjacent will be scaling cosine by the magnitude of a. Another way to think about it is using the fact that cosine is adjacent over hypotenuse and solving for the adjacent. Uh, but that's just this one piece of the dot product. Then you take that and you multiply it by b. So that's the reason we say that the dot product is a scaled projection. So you take this projection, which is this adjacent side of the triangle, magnitude of a times cosine, and multiply that by the magnitude of b. Uh, that is um, that can be done also in the reverse way if you take b projected onto a and then scale it by a. Okay, and so that's one of the ways to think about why a dot b is the same as b dot a. um, Now, how is that useful in practice? Well, we can use the dot product to solve various applications questions such as finding the angle between two vectors. Notice here I can solve for cosine will be a dot b divided by the magnitudes of the two vectors multiplied together. And to find a dot b, we can use the symbolic way of figuring that out. And this is also used by projection. This is the main way I want you to think. What is the dot product? If somebody asks you on the street, what is the dot product? Well, it's a scaled projection. You might say, oh, well, you just multiply the components and add them up. That's not really useful to somebody. Like, what does that do? If you multiply and add, it doesn't tell you much. But this way of thinking about it is it's like, oh, you're projecting and then you're scaling that by the magnitude of b. That's really the way to think about the dot product. And so to find the projection of a onto b, we need a vector in the direction of b that has magnitude being equal to this adjacent side of this triangle. And so we can think of the projection as being the adjacent side, that's the magnitude, times a unit vector in that direction. And so how do we get the unit vector in the direction of any vector? We'll take the vector divided by its magnitude. Okay, so b divided by the magnitude of b. Multiply here by b up and down. And we get that the top here is a dot P, and the bottom is P dot itself. This is a number times a vector. Okay, so the projection here, we're thinking of this as a vector now. And this part here, the coefficient, you can use the symbolic way of multiplying component twice and adding up to figure it out. For the, and so that gives you the projection, and work. To figure out work, well, you just do the dot product of force times displacement. That's the definition of work. Cross product it also has two ways of being represented. One is the geometric way, and one is the symbolic way. Symbolic way is basically you have some nice rule of how to cross multiply and add things up and subtract, and um, you can use this matrix representation to kind of figure out a nice way to memorize that. So that's the symbolic way. But again, you're doing all this calculation. What does it mean? What's the point of it? And the geometric way really tells you what does the cross product do. Well, the cross product has a magnitude that is the area of the parallelogram determined by A and B. So this black parallelogram here, and the area of that is given here. But then taking that and multiplying it by a vector in the direction perpendicular to A and B, okay, given by the right-hand rule. So if you start at A and you rotate towards B with your hand, uh, the thumb is going to point in the direction that's needed here. Okay, notice here one thing to quickly make sure you understand is that the dot product works for any dimension and it's a number, whereas the cross product only works for three-dimensional vectors and ends up being a vector. This is a crucial difference between the two. Otherwise, the formulas look kind of similar. We're doing multiplying magnitude times cosine, multiplying magnitude times sine. But this one is multiplied by a unit vector, so it ends up being a vector. This is a number. Okay. So why is this the area of the parallelogram? Well, drop the height here from the tip of A. And again, think about scaling this unit hypotenuse triangle from the unit circle. Scale it by A again. This is the side opposite to the angle, so that's the sine. That's scaling sine by the magnitude of A. And so the area of a parallelogram is base times height. The base is the magnitude of B times the height, and we get this formula. Okay, let's go here to solve one sample question. So we have here v, a vector v in the pointing in 512 direction, and we have another vector in the negative 3, 4 direction. What is the amount of speed that the train gains due to the gust of wind? So the train is on tracks. It cannot possibly get off tracks. Now, if u was pointing in the same direction as v, okay, if they're pointing in the same direction, then the amount of speed the train gains will be the magnitude of u. If you're given a velocity vector, its magnitude will be the speed that you gain. So that would be easy, but unfortunately they're not pointing in the same direction. U is pointing in some other direction. So how could we possibly figure it out? Well, think about taking U and decompose it into two pieces. So U is equal to the projection of U onto V and this perpendicular projection to V. Okay? If you sum this up, you get U. Now, this vector, this component of u that is perpendicular to v, doesn't add anything to the speed of the train because it's not like it can move the tracks. Tracks don't move. So the only thing that really matters here is u, is this component that is in the direction of v, the the projection of u onto v. So the speed will be the magnitude of that projection. And so that would be the dot product, take the magnitude of u times the cosine of that angle, but the dot product, you have also an extra magnitude of v multiplied there. So you have to scale it, you have to divide that by the magnitude of v to get back to just u, the magnitude of u times cosine of the angle between the two. And we can calculate this pretty easily. So u is 512, so 5 and u is negative 3, 4. So do negative 3 times v is 5 plus 4 times 12, and divide that by the magnitude of v. What is the magnitude of v? Well, v is 5 squared plus 12 squared. And this will be the speed that we gain. So you can put this into your calculator, and this would be the speed. Whatever the units are there, I'm not giving any units in here. If they were given, you just put whatever miles per hour that would be in there. And that's the sample question here, 1. Now,